I'm going to present a use case that we have done for cement industry. That is my colleague Matthias and myself, and we have called it the first ever innovative brownfield modification in cement industry, de-risked by smart simulation. And to emphasize a bit, first ever and modification and cement industry is somewhat a contradiction, because cement industry is one of the conservative heavy industries, and they are always afraid of doing something first ever, relying very much on references. But you will see in a minute how we, with a team of the plant, developed a modification and de-risked this by simulation. Well, just a few words to our company, to aixprocess. That was established in 2001. And it's still owner operated. We are located in Aachen in Germany. It's just at the border to Belgium and Netherlands. We are 25 in staff, 16 process, among them 16 process engineers, and in the meantime, nine data and machine learning specialists. And from our solutions, you see, and what I'm presenting today is the CFD and process simulation here. Then we have some digital solutions, but that is not the topic today. If we go to the industries, you see there is a broad variety of industries, among them cement. Cement, that is our brand name, XRG. And so don't be confused if we now change a bit in the colors to orange, because that is the background of our cement brand. All right, let's jump into the use case, and that is the Längerich plant in Germany, by Dückerhoff, cement producer. This plant in the middle north of Germany consists of two kiln lines, kiln 4 and kiln 8. So these are kind of historical names, and you see from the data those are quite different capacity wise and from their age. And the one I'm talking about today is the kiln line 4. Originally built in 98 and was 1980s, and was modified a few times. It's a Polysius kiln, preheater, and then baghouse filter were added afterwards. And what's important is the fuels. This is fired by lignite, residual derived fuels, and some solvents as minor fuels. So that is what we'll be talking about. What's the trouble? And if we are talking about brownfield plants, they typically have some troubles. This calciner was originally designed for lignite firing. That means 100% lignite. Although lignite is not one of the best fuels, of course, it's rather well defined. But although I mentioned that cement industry is kind of conservative, they tended years ago in Europe to decarbonize their production. That was not originally for mainly CO2 reasons. That was simply for cost reasons, just to substitute lignite or coal by residual fuels, sometimes even with a gate fee, so they would get money if they take those fuels. That's not the case today, but still any kind of alternative fuel is significantly cheaper than lignite or coal. This calciner, and for those who are not familiar with the cement process, I will shortly explain. The calciner is a kind of entrained flow reactor. You can see here the end of a rotary kiln. Typically, the rotary kiln extends to some 40 to 60 meters. And here we have a duct, an upward duct with in the order of magnitude of 4 meters in diameter. And you see a bit of complex geometry on the top that is for mixing purposes. And there are several ports for injecting the raw meal and the fuels. And this one, this calciner, is a relatively short calciner in terms of retention time. So the retention time, or the average retention time of the upflowing gas and fuel particles is about 2 to 3 seconds. But particularly this calciner suffered from exceptional CO emissions under the injection of typical fluffy material, fluffy RDF fuel. And still, when the plant applied a more expensive fuel, that is a pre-ground RDF and pelletized and pre-ground RDF, they still had elevated CO emissions, as you can see from the picture here. So here is the 1,000 milligrams per normal cubic meter limit, and so there are, and these are monthly averages. So that is high. It's too high to have permanent operation. So that was one of the reasons to do a retrofit here. And completely coal-free calciner operation is not possible, although the plants tend to thermal substitution rate, at least in the calciner, of 100%. And so the target of the project, of the retrofit project that we were able to support, was make the calciner ready for 100% TSR with low CO emissions. You remember that in the title, we named it smart simulation. So what is smart at this in this kind of simulation? With this material, which you can see here, this is this pre-ground RDF pellets. And just I go one slice further, and this is the fluffy RDF. You see that is everything different than a solid particle, a sphere. And so it's really difficult to categorize these fuels by the typical data we need for a simulation. That is particle size or particle size distribution, density, maybe particle shape. So what we did as a kind of change to the categories of particles is that we categorize them by terminal velocity. That is a method that was published elsewhere. If anyone is interested, we can give the reference. So these particles are injected into a zigzag sifter, and terminal velocity is determined, and we did the same with simulation. And again, you see it's a Barracuda simulation to identify the typical terminal velocities and to transfer them into sizes of particles that we can use as an input for the simulation. Yeah, I didn't really mention Barracuda yet, because for us it's more than natural to do these simulations in Barracuda. The reason being, although the average particle concentration in this entrained flow reactor is something about 1 kilogram solids per kilogram gas, there are, particularly at the meal input and the fuel inputs, we have a real dense flow, leading to typical clusters of particles, typical transient behavior, as you will see in a minute. Particles are reacting, and so we have dense reacting particle flow, where Barracuda VR is still the best choice to use in the simulator. So going to these velocity distribution. So it's not a size distribution, it's a particle velocity distribution. You see that we have the RDF pellets in yellow and the fluffy RDF in blue. These pre-ground pellets, they require higher minimum gas speed for safe pneumatic conveying. And the coarse particles, of course, burn slower and produce more CO than the fine ones. And so the question in the beginning was, why is this particular calciner producing less CO with the pellets? That was not clear even after some operational trials. So the insight which Barracuda gives from the current operation, and that of course is the typical starting point, are these particles here, and we color them not by size, but by a scale hard to suspend in red and easy to suspend in green. And what you can see from the motion here is, I hope you can see it, these hard to suspend particles, they rain out into the kiln inlet. What they should do is be suspended in an upflow, reacting during the upwards flow like the green ones do. If we transfer this in a CO concentration, you can see here the typical CO streak as an input coming from the kiln inlet. That is unavoidable for the rotary kiln operation. But what you can see here, that is a layer of particles, of these big particles raining out into the kiln inlet and building almost a kind of fluidized bed of pelletized particles in this inclined part. So here, this is a permanent CO source. And if you look further to the upward flow, then you see there is a clearly segregated flow and a kind of stratification of CO and an O2 rich streak. So there is no real mixing in the riser. And that is the reason for these bends and kind of post-combustion chambers to induce turbulence. So you see there is some CO oxidation in this double deflector, but still the CO emissions are beyond 1000 milligrams per normal cubic meter. So second thing we did in terms of a smart simulation, if we may call it so, is that we did some combustion of these RDF particles. Because when we model it, of course, we need some kinetics for that. And since this is a broad variety of different materials and particles, that's difficult to get. So what we did is some combustion trials of different particles, and again we did some categories by hand, and then we found from different samples or sample categories different types, more or less 2D or these 3D fibers, different sizes, and then we could correlate some intense flames in orange, weak flames, and char conversion in red as over time. And that gave us, in the end, a kind of gross combustion kinetics. Of course, that is not precise, but it serves as an indicator for the behavior of this very heterogeneous material. All right, and after we had this troubleshooting analysis done, or the analysis done, we sat together with the plant team and really did a kind of brainstorming or conceptual phase. And what's clear is that the CO emissions can be reduced by increasing temperature, improving the oxygen availability for the fuel, enhancing retention time for the fuel. But you see, increasing temperature is difficult from overall energetic point of view. Enhancing the retention time, well, yeah, that is to some extent possible. But of course, in a minor retrofit, the customer doesn't want to change the diameter of the upwards of the riser. So retention time is clearly limited by for the fluffy RDF, because it's suspended, it's going with the gas flow, so there is no chance to decouple this from the retention time. But we thought of the coarse particles, these high dense particles producing a lot of CO. And what we really sketched, and this is really a copy from our workflow, that we did a kind of combustion chamber, and that is exactly what was never done before. There is no example from each and every riser. There are of course a lot of combustion chambers available on the market, but they are kind of standard, and this one is tailored to this particular calciner. So this concept was developed by the Lengerich engineers, of course, with a little support from our side. And okay, we have the simulation in hand. Now let's see what does it do. Yeah, and again, you see the particles moving. And you see here this humpback combustion chamber. Well, you hardly can see any big particles falling down here in this inclined section. A few do, yes, but the main part is suspended and going up. CO concentration turned out for the pre-ground pellets, in this case, to be much lower here. Streaks being smaller compared to the former design. And the overall concentration at the top significantly lower. And from values, it's 70% compared to the former operation. What does happen with a fluffy RDF, which is even harder to combust? Again, we see that it's technically feasible. CO emission slightly increases compared to the pelletized RDF, but still there is a significant reduction of CO emissions by 60%. And that will mean the fuel costs expenditures are drastically reduced, because you can use the cheap RDF fuel compared to the pelletized and tailored fuel. Okay, this is just what we did for the Lengerich engineers. This is a bit of flow of this device. So here you see this combustion chamber. And you see the meal dropping down from the top and being suspended. And now we turn to the lower part. This is where the fuel is suspended, going round and round and round. So with a much higher retention time for the coarse particles. So, the truth, of course, is in the end in reality. Here's the outcome after the retrofit. You see, it was done in summer in 2018. And this are the history values of CO emission. And immediately after installation and startup of this new installation, the emissions were reduced by 70 to 80% after startup. And I can tell you they remained even now after almost 4 years of operation and at the same range. There have been some issues. We experienced some hotspots at the roof of the combustion chamber, which could easily be solved by injection of cooling meal. that is rather typical or rather normal in cement industry. If they detect a hot space, they are using a bit of cool meal and inject it. These are minor retrofits done at the next revision, so not really a failure of the design where we did. Yeah, and what is the economical benefit? The total substitution rate could be increased by 22%. That meant a reduction of fuel costs through the substitution of lignite by RDF of around 1.4 euros per ton clinker. Then there was an additional reduction of fuel costs due to the elimination of the pre-ground pellets. So using the easily available RDF made another euro per ton of clinker. So the total fuel costs 2.4 euros per ton clinker, and that meant a return on investment in less than 6 months. And the invest here was the study costs, that was the retrofit cost, and well, you can tell that retrofit even was more than our study costs. But still, that is something that paid back in the first year after installation. Take-home messages from that. These CFD studies, or CPFD studies, have proven to be exact in a way. Not really, they are not verified, you saw. Well, we have done some assumptions of terminal flow to characterize these heterogeneous particles, the heterogeneous fuels. We have done some simplifications in kinetics. So we are sure that is not an absolute prediction of what is happening. But still, we have a reference from more than 100 projects in cement in similar cases, that they are exact in a way to project the future effects compared to what's happening today, even for minority components like CO, which is always tricky to model, and even in homogeneous combustion. Well, due to the lack for reference for this real equipment for this combustion chamber, there was the only possibility to make use of detailed modeling or smart simulation to check the feasibility or viability of this unique proposal. The proposal itself, the retrofit, has proven to be successful, like the CFD saying, do it right the first time by using detailed modeling. And the project objectives could be reached. Project effect is increasing TSR, reduce the CO emissions, and save fuel costs. Yeah, well, the additional benefit to downgrade the fuel that is used, that is an important aspect in terms of availability of these fuels. This careful engineering has led to a total project success within an ROI of 6 months. And there are other examples of this small modifications in suspending the material, either meal or fuels, to bring them in the right ratio and to combust and transfer the heat. And well, as far as we see it, for the time being, still the best and reliable software to do this, well, not only in fluid beds, but in these kinds of entrained flow reactors, is still Barracuda VR, and that is the reason why we are relying for these simulations on the software.